So I will try to introduce the construction of closed string field theory. So string theory is a framework. So although we call it as a theory, it's not a specific theory, it's a framework. And this framework has a capacity to combine the principles of quantum mechanics and the principles of Einstein's theory of gravity. Or gravitation. So if you use the quantum field theory formulation or the quantum field theory framework, it's not so easy to combine these two pillars of theoretical physics. But string theory provides you a way. And the conventional definition of string theory is a perturbative definition. And what it does is, you can think of the usual definition of string theory as the world sheet or the world line analog of quantum mechanics of point particle. So what you do in string theory is, instead of considering point particle, you consider strings, and when a string propagates through a space-time, it traces a world sheet. So these are the, so instead of world line, we study the world sheets. So like in usual quantum mechanics, you can consider the scattering of different string states. So let's say you want to consider n1 number of states, and they interact, merge together, and then provide you a set of final states, say n2 number of final states. And you want to know what is happening here. So you know the external states. You have n1 number of string states, they somehow interact and then provide you n2 number of out states. And in quantum mechanics or in quantum field theory, you come up with a prescription that gives you what is the amplitude for this process. And string perturbation theory gives you a prescription for computing the amplitude for this process without referring to any Lagrangian. So that's the main point. You don't have any Lagrangian. A space-time Lagrangian. But still you can define or come up with a recipe that computes the amplitude for the scattering process. So the main object in conventional definition of string perturbation theory is amplitude. So you have to somehow give you a way to define the processes inside this blob. What happens here? So you should tell us, or somehow you should come up with a prescription that tells you how the strings are interacting. So the way you define interaction in string theory or perturbative string theory is very simple. What you do is you consider, say, 2 or more number of strings, and then allow them to interact. When they interact, they merge together and then give you a single string. And then this intermediate single string can again produce a set of another strings, and this happens again and again. So at the end, what you get is a world sheet having some number of handles and some number of external states in it. So this way you can produce all the Feynman diagram analogs in string theory. So these are the string diagrams. So you can compare it with the diagrams like this. But the main difference is that when you draw a diagram like this, so it's a single Feynman diagram. But when you draw a string diagram, it corresponds to several Feynman diagrams. So let us consider a diagram like this. So you can see that this diagram can be, I mean, you have if you take the point particle limit, you get this kind of diagram, or you could place this loop some other side, and you can get another diagram. So basically, this diagram has a symmetry, huge amount of symmetry. So most of the diagram looks similar. But the main point is that amplitude or the string diagrams or the prescription in string theory provides you an object, and that object, if once you take the point particle limit, corresponds to several number of different Feynman diagrams. So you don't have to go to this point particle limit for defining string amplitude. So what you do is you work with the string diagrams. So you start with this diagram, and the only condition that you have is you know how many external states are there, and allow all the possible diagrams that you can draw with this particular number of external states. So that is equivalent to saying that if you want to compute the scattering amplitude for a process like this, you have to consider all possible connections that give you a world sheet. So you could have a connection like this where you have no handles in it, or you could introduce a number of handles here, and you are supposed to sum through all possible such world sheets. And the number of handles that are there depends on how the intermediate state propagates. So depending on the way intermediate string propagates, you can convert the sum over all world sheet into a sum of into a series. So you can start with diagrams having no handles. Even if you have a diagram with no handle, still you have infinite number of possible world sheets. What is the interactions parameter? The perturbation parameter is a string coupling. So you don't have any, actually in string theory you don't have any free parameters like you have in quantum field theory. Everything is uniquely determined. And the string coupling itself is something that's related to one of the excitation in string theory. So you don't have any free parameters. But still you can go ahead and then define a sum over world sheet and then try to reorganize the sum over all possible world sheet. So the first thing what you can do is, say if you want to compare with the usual quantum field theory, you can try to convert this sum over all possible world sheet into a sum over different number of loops. So this is a class of diagram. So still, although you don't have any sum over handles, you have infinite number of world sheets. I mean, right now I haven't. I mean, I can't really count it, but naively I can say that there are infinite number of world sheets, depending on how I change the surface, and I should tell you how I change the surface. So let me don't get into that detail. So you have a sum over handles. Basically, you start with a diagram having no handle, and then you have diagrams having single handle, and then it goes on. And what string perturbation theory says is that how to really deal with each summation. Polyakov studied this summation carefully, and so if when I say that there are infinite number of world sheets and then sum over this diagram, it's not very well defined. So what Polyakov did is he did a careful analysis and then showed that this can be converted into a sum over all possible Riemann surfaces having specific number of handles. Say h number of handles are here. Moreover, this summation, like I said, it reduces to a Riemann summation of a Riemann surface. On the top of it, you have to consider a particular conformal field theory on each Riemann surface. So you have a CFT on each Riemann surface having, say, h number of handles, and each world sheet come with, like, when you do the path integral, when you do the sum over world sheet, so you have a phase factor, which is the Polyakov action, and with this phase factor, this summation reduces to a sum over all possible Riemann surfaces having particular number of handles. And moreover, the external string states can be mapped to a particular operator in this world sheet conformal field theory. Say you have a particular state having quantum number ai, then the state operator mapping says that that string state can be thought of as a specific operator, which people usually call as vertex operator in conformal field theory. So now the precise prescription for computing this scattering amplitude is as follows. So you take the vertex operator corresponds to all external states, say VA1 to VAN, where n is n1 plus n2, and then you have to introduce some pieces that corresponds to ghost part of the conformal field theory, and then compute the correlation function of these vertex operators in a particular conformal field theory, and you have to sum over or integrate over all inequivalent Riemann surfaces, and the space of all inequivalent Riemann surface is known as the moduli space. Moduli space for a particular Riemann surface having particular number of handles, and then sum over the handles. So this is the way you compute a scattering amplitude for the scattering of n number of external string states. So this is what usually people call as Polyakov prescription for computing. Scattering amplitude in string theory. So here we don't really use any Lagrangian, but this prescription works if you assume certain things. So this definition is consistent only if you assume that, say, the mass of the or the momentum for the external state satisfy the classical on-shell condition. So Ki is the momentum for the ith state represented by the vertex operator VAI, and say the mass for the classical or the tree level mass for this state is, if I denote it by MCI, then the external momentum should satisfy the classical on-shell condition. So it should be k square plus m square should be equal to 0. So you have to impose classical on-shell condition for all external states. So that's one condition, and one can see why you require that. So here you have a particular operator in a CFT, and each operator in a CFT has a particular weight, and that weight corresponds to this combination. And if you have a finite weight for the vertex operator, the whole object will start depending on additional data that you have on a Riemann surface. On a Riemann surface, you can define or you can choose a particular parameterization, and choosing particular parameterization on world sheet has no physical meaning. So if I choose momenta or generic momenta which doesn't satisfy this classical on-shell condition, that's equivalent to considering vertex operators having non-zero weight. When you have non-zero weight, the whole object will start depending on the way you parameterize your world sheet. And that's not consistent. So that's not physical. So what people demand is that when you compute this, you are computing a physical object, a scattering amplitude, which should not depend on any unphysical data. So demanding that is equivalent to saying that you have to demand classical on-shell condition for each state that participate in the scattering process. So that's one condition. The second condition is that the whole integral makes sense only if you assume that the string is the space-time through which string is propagating satisfies certain classical equations. So the background space-time through which the string is propagating must satisfy certain classical equations. Usually this is seen as a victory. So you can see that, so these classical equations are kind of generalization of Einstein equation. So we see that we say that you can start with strings and demand that the theory has Lorentz invariance that naturally lead us to a particular background spacetime, and that condition can be thought of as a certain classical equation. But when you start doing the perturbation theory, still you have to demand that the background must satisfy certain classical equation. Only then this object can be thought of as something that doesn't depend on any unphysical data. So the usual Polyakov prescription or the conventional formulation of string theory requires that all external state that participate in the scattering process has to satisfy a condition, a particular condition, and the background through which the spacetime is, or the background through which the string is propagating should satisfy a set of classical equations. But when you do quantum mechanics, you know that you can't fix anything classical unless you have a certain symmetry. If you don't have a symmetry, say in generic situation, mass of an external state that participate in a scattering process get renormalized. So the initial mass with which you started in perturbation theory won't stay there. Masses will get correction, quantum corrections. Moreover, the spacetime through which the string is propagating also will have corrections. So you will have correction to the mass of the state, and also you will have correction to the background spacetime. And when you have correction to the background spacetime and the mass of the external state, you have a problem. The problem is the following. Say if you have some renormalization happening in your calculation, and if you blindly fix the momentum of the external state, definitely that gives you infrared divergences. So fixing a background or fixing a classical condition when you do quantum mechanical calculation usually lead us to infrared divergences. So for example, you can consider this diagram. Assume that you have a diagram where three string states are interacting, say V1, V2, and V3. And the first condition demand that, say you start with a vertex operator having tree level mass m, and then you want to consider only those momenta that satisfy k square plus m square equal to 0. So when you compute this diagram, you have a piece here, and that piece comes with a propagator factor 1 by k square plus m square. So when you demand that k square plus m square equal to 0, that's equivalent to saying that the whole amplitude that you computed diverges. So this is the infrared divergence that comes because of the unphysical or unphysical condition that you demand on the external state. In fact, quantum mechanics is the one which tells you what should be the correct quantity. it's not yours. You are not supposed to demand any classical condition. The classical conditions are preserved only if there are certain symmetries that allows the object to not get renormalization corrections. So only if you have additional symmetries, you have a classical condition that's not affected by quantum correction. But that's not a generic case. So the point is that if you demand all these two classical condition, you will have trouble. So I just told you an example where you see how the first condition is going to introduce IR divergences.
This IR divergence seems to be there in the field theory also.
That's true.
Not really as
Yeah, so that is true. But when you do computations in quantum field theory, you never demand that k square plus m square equal to 0, right? So you demand that k square plus m physical square should be equal to 0.
So if you agree that we are even in string theory, we demand only whatever we demand in field theory.
Yeah, then we are fine. But then you have a trouble here. So you demand that if you demand that k square plus m c square is not equal to 0, that's equivalent to introducing vertex operators having finite conformal dimension. Then that will introduce dependence to the spurious data such as coordinates on Riemann surface. So that means whatever you compute here won't be a physical object. But your claim is that what you compute is a physical object, which is the scattering amplitude. So you have a trouble here.
You also mentioned that that diagram you drew.
Yeah.
In the field theory limit.
Yeah.
This is one of the diagrams, but that also is equal to many other diagrams.
I mean, sum of all diagrams.
Yeah.
Yeah.
So if you take the sum of the IR diagrams, will still persist. With that diagram.
Yeah. Still, I mean, the point is that each diagram, when you do the computation for each diagram, you have to impose this condition. So each diagram will have a divergence. Yeah, you sum over all this Feynman diagram, and there is no reason to believe that all those will cancel each other. I mean, the divergence will catch. No, in general case, like I don't see any reason why two diagrams should be connected, right? So cancellation happens only if there is some connection between. See, I mean, you can expect, but I mean, when you take the field theory limit, you see independent diagrams, and you don't see any relation between them. So that itself will say that, I mean, you can find relations if you have symmetries. If you don't have relations, or if you don't have any symmetry, they won't. The divergence coming from each diagram won't cancel each other.
Yes, the face of it, they won't reflect the cancel.
Yeah, that's true. But this situation happens for cases like massless, the scattering of massless particles. You have such divergences in each diagram, but due to the symmetry, the gauge symmetry, these diagrams are related to each other, so that the infinities will cancel each other, and you get a finite answer. So otherwise, it won't happen. So you can take the same string diagram and look into another field theory limit. So where you have a diagram like this. So this is the tadpole contribution. So you have a state propagating along direction, and then it just come back. It definitely is not a, I mean, it doesn't look physical, but you can have such a diagram. And this diagram again have a difficulty. So if you have a massless particle propagating, then the massless particle will satisfy k square equal to 0 condition. And then from this propagator, you will get a infinity. And these diagrams, which are usually known as tadpole diagrams, comes whenever you have quantum correction to the background. So again, you have to somehow regulate it. And the usual formulation, the conventional formulation, won't give you any prescription for really dealing with such divergences. In quantum field theory, you have a prescription. The prescription is that you have to go off shell. You compute Feynman diagrams, assuming that all the external states have off shell momenta. Then all of these divergences can be regulated, and show that at the end, none of the physical objects have any divergence coming from infrared region. So the point is that the usual formulation of string perturbation theory is not satisfactory. It's satisfactory only in the tree level. Since in the tree level you don't have any loops and you don't have any quantum corrections. But beyond tree level, you will have trouble. So you have to come up with a prescription that's better than the usual conventional formulation of string theory. Or somehow you have to come up with a way to really resolve these puzzles. So like we discussed, if you go back and look into quantum field theory give you a way. What it says is that you have similar diagrams even in quantum field theory, but you control those divergences by assuming that the external states won't satisfy any Marshall condition. So you have to somehow come up with a well-defined prescription for off-shell amplitudes in string theory, and then show that when you compute physical objects, the final answer should not depend on any unphysical data such as choice of coordinates on the Riemann surface. So that's the task. So you can start with the string diagram like this, and then we see that if we have some way of decomposing the sum of string diagrams into different pieces, and we should somehow be able to identify each pieces with certain divergences. If you can do that, then you could throw out that piece from the string diagram that has a divergence and then look into the piece that doesn't have any divergence, and then identify.
Even the fact that you might be able to do itself is not clear, right?
Yeah, that's true. It's not clear that you can really decompose the string diagrams into pieces that has Feynman diagram. Yeah, it has problem, but the problem is there only if you demand on-shell condition.
This example that you have, you can isolate Feynman diagrams.
Right.
But in other,
Yeah.
probably it's not even clear that whether it's possible to isolate the limit of various.
That is true. So it may not be possible, or at least you don't see a simple way of decomposing the moduli space integration into different Feynman diagrams. So the idea is the following. So if you can somehow come up with a definite prescription that decomposes the moduli space integration, basically the string amplitude, into different contribution that corresponds to Feynman diagrams, then you can regulate the IR divergences. So you want to come up with Feynman rules for string theory. Is it possible to define Feynman diagrams for string theory? And then somehow we should be able to reconstruct the string amplitude from those Feynman diagrams. And you can do that. So the idea is to look for a way that constructs Feynman diagrams for string theory. So here I am literally talking about Feynman diagram, not the string theory analog of Feynman diagram. So you can construct Feynman diagram if you have a quantum field theory that describe the dynamics of string theory or string diagrams or the interacting strings. So if you have a quantum field theory that defines or that describe the dynamics of strings, then you can regulate these IR divergences. Then you can define what you really mean by a Feynman diagram in string theory. And you have such a quantum field theory, and that's string field theory. So string field theory is a quantum field theory that describes the dynamics of interacting strings. And you can define the Feynman rules for string, or you can derive this Feynman rules for string field theory and use those Feynman rules and the Feynman diagram to reconstruct the string amplitude. So the idea is that use the Feynman diagrams or Feynman rules of SFT, string field theory, and then that will reconstruct the string amplitudes. Here the point is that the amplitude that you construct from the Feynman rules of string field theory formally agrees with the scattering amplitudes in conventional string perturbation theory. So I say that they agree only formally because conventional string perturbation theory give you amplitudes that are not well defined at some time, right? In certain cases, the usual string perturbation theory give you consistent amplitudes. Whenever you get consistent amplitudes from string perturbation theory, that matches with whatever you compute in string field theory. But when you have trouble in string perturbation theory, string field theory compute correct amplitudes. So that's why I say that they formally agree. So I think of string field theory as a consistent definition of or consistent definition of string theory. So this is consistent even if you have mass renormalization or vacuum shift. So the basic idea of this lecture series is to tell you how to really construct the string field theory or get the consistent definition of string theory.
You mean consistent definition of full string theory and not just part of it is string theory?
At least I should be able to get the correct perturbative definition of string theory.
But apparently you don't expect that it should recover all the dualities of the phase.
If you have a quantum field theory, in some sense is a non-perturbative definition.
Yes.
Whether you can really use that quantum field theory to get the full non-perturbative information or not, that depends on whether you will be able to solve that quantum field theory. Right? So if you can solve string field theory, the expectation is that you should be able to get the full definition of string theory. Even the duality you should be able to recover. But that depends on whether you can solve the theory or not. If your string field theory is simple, then you can solve and get non-perturbative information. And if your string field theory is very complicated, then just like in usual quantum field theory, right? So you have standard model and you don't know how to really solve it, right? You haven't solved the that's true. You haven't solved the confinement directly from the standard model, right? So the situation is same. So that depends on what kind of string field theory you really get. So the basic idea that I want to convey was that string field theory is not just a fancy subject, it's a necessary thing to do. Like if you want to do string perturbation theory. And so I said that string field theory is a quantum field theory. And we know that string theory has excitations that are gauge fields. So you have usual photon-like gauge field, and you have gravitons, which is again a gauge field. So you expect that string field theory must be a complicated gauge theory. Even gravity itself is a complicated gauge theory. So what you have is a gauge theory that describes the dynamics of interacting strings.
You have to forward it in critical dimension, or you can forward it in any dimension.
So right now I'm going to just look into critical dimension. Yeah, otherwise I have difficulty in defining the conformal field theory and then getting rid of the So this reducing to Riemann surfaces may not be sensible. So I'm going to look only into string field theory that are defined in critical dimensions. So you have a gauge theory and you want to construct that gauge theory or quantize that gauge theory. So the gauge theory for our situation is string field theory. But before getting into string field theory, we should understand the quantization of gauge theories. So the classic example of gauge theory is electrodynamics. So in electrodynamics, you have electric force and magnetic force, and you think of electric and magnetic force as interaction of photons, and photon is a spin one particle. So you have a vector potential there. So this vector potential has 4 components, and we know that only 2 of them are physical and 2 are unphysical. We still keep these 2 unphysical degrees of freedom to show to explicitly show the Lorentz invariance of the theory. So, or you want the manifest covariance. So when you have unphysical states, and if you try to quantize a theory, you get states that have negative norms or non-positive norms. So to get to really, so that's equivalent to saying that you seems like you have a non-unitary theory. To make the theory unitary, you have to introduce additional ghost field. So once you introduce ghost fields, the contributions that comes from this negative norm states will be cancelled. So the full theory is covariant plus it's unitary. So the basic idea is that when you look into gauge system, you have a less number of you have certain number of physical degrees of freedom. With that physical number of physical degrees of freedoms, you won't be able to explicitly formulate theory that has, a theory that has explicit covariance. So you want to add additional unphysical degrees of freedom, and then adding unphysical degrees of freedom introduces a difficulty. Basically, you get negative norm states, and then you want to get rid of that difficulty by adding extra fields. These are the ghost fields, and we call them as ghost fields because they won't satisfy the spin statistics theorem. So this is the configuration with which you start. So you have a classical system and you want to quantize it. So how will you quantize it? So when you look into a simple gauge theory like electrodynamics, the gauge structure is very simple, so that the ghost field effectively decouples from the physical sector. So you don't really have to worry about the ghost fields. But when you consider non-abelian gauge theories, you will have ghost fields which are interacting. So they won't decouple from the physical sector. So it's not so easy to quantize them. So you have interacting ghost fields. So when you look this system from the point of view of path integral, the ghost fields come from the measure. So you can think of the ghost field as a measure effect. So you have a path integral defined as integral over certain number of fields with action. And you want to make sure that this integration is well defined. You want to have a finite answer for this path integral. So you have to do gauge fixing, and during that process you pick up transform Jacobian factors, and that Jacobian factors can be thought of or replaced with interacting ghost fields. So you start with a Lagrangian L, and at the end you replace it with L plus gauge fixing piece and ghost fields. And you want, and at the end, you want to quantize this theory. Theory having modified Lagrangian, L plus L goes L gauge fixing piece, and Lagrangian for the gauge fields. So when you reach up to this point, even after gauge fixing, you see that there's a global symmetry. That, remember, the gauge invariant. So that's the BRST symmetry. So it can be thought of as the residual piece of gauge invariance. So this is a global symmetry. And you want that the theory is invariant under this global symmetry. So you have a BRC symmetry. So you gain BRC symmetry starting from scratch, and then did the gauge fixing and added enough number of gauge fields, and you saw that still you have a symmetry left over. It's not a gauge symmetry, it's a global symmetry. And when you have such symmetries, it introduces relations among correlation functions. So you can compute correlation function for the theory having this modified Lagrangian, and you know that you have a certain symmetry for the combined system, and that induces certain relations among correlation functions. And these relations involve insertions of BRST variations. So usually when you have such insertions, it's useful to introduce source for the such insertions. So the idea is that if you can introduce source for BRST variation, that's convenient, and that will help you to really utilize the BRST symmetry. So I made a statement, and then I would like to go through an example and show what do I really mean by that. So I would like to now I would like to really show a structure in this theory. So let me start with a non-abelian Lie group G. So look into the Lie algebra for this group G, and I denote the generators as T alpha. And alpha is an index that runs from 1 to the dimension of the group. And I assume that the Lie algebra is closed one. That means if I consider the commutator of two generators, that again produces another generator. So this is a simple Lie algebra, in the sense that you can consider gauge group that has more complicated structures that's more complicated than this. So this kind of gauge group are usually known as closed algebra. We are going to discuss the quantization of a closed algebra. So you have a particular Lie algebra, and you can look for a representation for the Lie algebra. So let me call, or let me denote a representation by R. And by finding a representation for this Lie algebra is equivalent to saying that you want to find a set of matrices that satisfy this commutation relation. So you have a generator T alpha, and then you can find the representation T alpha R. So this is a matrix having dimension R cross dimension R. So this is a square matrix. So that's what you mean by finding a representation. Now consider a number of matter fields. Say psi L. And again, you can find or look for a representation for these matter fields, because these matter fields will transform under the gauge transformation. So once you have such a gauge system, you can write down the gauge invariant Lagrangian for this. And then try to quantize it. The gauge invariant Lagrangian, or classical Lagrangian for the system, where you have a gauge field A mu and matter field psi, given by the gauge invariant combination F mu nu alpha F alpha mu nu plus a piece that corresponds to the Lagrangian for matter field. So here d mu is the covariant derivative defined with respect to the gauge field A mu. So what you want to compute in this theory? So you want to compute correlation functions for a set of gauge invariant operators. So you have gauge invariant operators O1 to On, and you want to compute the time order correlation functions. And you can define this time ordered correlation function using path integral, and that's given by a constant into path integral over dA mu and a function b f a mu. I will explain what is this function b, and then a piece determinant of f a mu and g a mu. I will explain each pieces. The f alpha, or the small f alpha, is the gauge fixing function. Demanding f alpha a equal to 0 is the gauge fixing condition. And this piece, determinant of f, that's a Jacobian piece. So you can start with a and then do a gauge transformation and get into a configuration a prime, and then you can compute what is the Jacobian corresponding to that infinitesimal gauge transformation, and that's what you mean by this piece. I will tell you. And b of f means a product of delta functions. So you have a delta function that corresponds to gauge fixing f alpha equal to 0, and then you have to do the gauge fixing at each point on the space-time. So it's a multiplication over each points on the space-time and for the components alpha. So this is the Faddeev-Popov prescription for computing this time ordered correlation function, and G A mu is a path integral performed over the matter field. Now Faraday-Popov theorem says that you can choose any f and any b. That won't change the final answer for the time ordered correlation function. So when you change the gauge fixing function, nothing happens. When you change the function b, then that will introduce some irrelevant constant. So physically nothing is going to happen. If the definition for the time ordered correlation function is independent of the definition for small f and the function b. I could have chosen some other combination.
How can you change b? I mean, you are saying that I can keep f fixed but change b. What does that mean?
I mean, I could choose another, instead of delta f alpha x, I could choose another combination such as 1 by epsilon or I by epsilon f alpha. And that's why it's a theorem. It's not so simple to see. I mean, you can derive, it's not very hard. So that's a non-trivial statement. You can, I mean, the natural guess is that you should always use delta function. But you can use function that's not just delta function. So that's the power of Faraday-Popov theorem. And when you usually quantize the gauge theory, you hardly choose this kind of gauge fixing. You always choose this kind of gauge fixing. Now it's again a standard thing that you can convert this determinant into a functional integral. So you can introduce ghost field into this path integral instead of having this determinant piece. And then once you integrate out that ghost field, you should reproduce the determinant. So that's one observation. So the statement is the following. So you have determinant of f that's equal to a functional integral over d omega and d omega star. This omega and omega star are independent real parameters or real fields. So they are anti-commuting, but they don't have half spin. So that's why these are ghost fields. They don't satisfy spin statistics theorem. But it's useful to introduce them. So that's one observation. So you can see that. So the determinant piece will go to the exponential part, and that will add up with the Lagrangian, the original Lagrangian that you had. So that's how you get ghost contribution for the modified Lagrangian. And once you and for the gauge fixing parameter, so when you choose a function beta of this form, that again goes to exponential. So that's the way you get a gauge fixing term for the Lagrangian in the modified Lagrangian. So this way you start with the classical Lagrangian and you introduce ghost contribution and the gauge fixing contribution. Now before analyzing the BRST symmetry, you can go ahead and then add one more additional auxiliary field, so which I denote by H alpha. So the statement is that I have to replace this piece with another piece. So let me write it. So instead of using 1 I by epsilon f alpha or I by theta f alpha, I can use another piece in the Lagrangian. That's again epsilon by 2 h alpha f alpha. So this piece will be there in the Lagrangian. Now when I integrate over h alpha, I should reproduce this part, this term. So that's a statement. So it's not necessary to introduce auxiliary field, but that's convenient. So once you introduce auxiliary field, the system will have matter field, gauge field, gauge field, and the gauge fixing term in the Lagrangian, and moreover you have an auxiliary field H alpha. So you get a new Lagrangian, and we will analyze a symmetry for this new Lagrangian, or we will observe a symmetry. So the L nu, after doing all this exercise, you get L as L plus H alpha H alpha H alpha F alpha plus omega star alpha into rho alpha. So rho alpha should be chosen in such a way that you produce the correct gauge field contribution to the Lagrangian. And here L is the classical piece, or the Lagrangian with which you started. So this includes the Lagrangian for the A mu and the Lagrangian for the psi field. So now once you obtain this new Lagrangian, you can observe a certain a symmetry. So when you do the following transformation, delta theta A alpha A mu alpha to theta where theta is a anti-commuting parameter, C beta gamma.
Rho is determined by this F.
Right. Basically, omega star alpha rho alpha is precisely this expression. So now you can consider the variation of gauge field with a anti-commuting parameter. So when you consider this, I'm going to define a delta theta variation using this relation. So delta theta A alpha A mu alpha is equal to theta into del mu omega alpha plus C beta gamma alpha A beta mu omega gamma. And then I should vary psi also. Del theta psi equal to I theta omega alpha T alpha R psi, and delta theta psi dagger equal to I theta psi dagger T alpha R omega alpha. So this invariance of the new Lagrangian is what you call as BRST symmetry. So this is the BRST transformation. So you can observe that this is precisely like the or this is the gauge transformation for each fields in the original Lagrangian. So the only difference is that you replace the gauge parameter with theta into omega alpha. To start with, you didn't have any ghost field. So you replace the gauge parameter with theta into omega alpha. So you know that omega alpha is an anti-commuting object, and theta is also an anti-commuting object. So together they form a commuting object. Huh? Yeah, that's true. Again, even if you don't do anything, you have this invariance. Now, for convenience, you can introduce a fermionic operator. S. So the fermionic operator S is defined as delta theta of F, where F is or H. H is a function of all these fields. This is equal to theta into operator S acting on H. So we introduce fermionic operator S for convenience. So you can observe that the delta theta variation is a bosonic variation. The operator X induces a fermionic variation. So that's actually convenient. Although the BRST transformation is bosonic, you can dig out a fermionic operator out of it. And that's how at the end you see BRST operator as some odd operator. Huh? Oh, this is the ghost field that I introduced to replace the determinant factor. So when you introduce this fermionic operator S, it's much more simple to write down the BRST variation. In terms of S, the BRST variation takes the following form. S of A mu is given by del mu omega or d mu omega. S of psi is just I omega psi. S of psi star is just I psi dagger omega. And you can also introduce BRST transformation for the ghost field and the auxiliary field. So that's given by S omega equal to I omega omega and S omega star equal to minus H, and S acting on auxiliary field H is 0. So now it's not very hard to check that this transformation is a symmetry for this new Lagrangian. And this is the BRST symmetry. Now it's not very hard to check that S is an nilpotent operator, S square equal to 0. And it's again easy to check that S acting on the new Lagrangian is 0. Even S acting on the old Lagrangian is again equal to 0. The reason is that the classical Lagrangian is gauge invariant. The BRST transformation can be thought of as a gauge transformation. So the classical Lagrangian automatically satisfy BRST symmetry or BRST variation.
It is global because theta is constant.
Theta is constant, right? Now the interesting observation is that the new Lagrangian is related to the old Lagrangian or the classical Lagrangian in a simple way. It has an interesting structure. So you can write L nu as L of L plus L is the classical piece or the Lagrangian for the matter field and the gauge field plus S into psi. S is the fermionic operator that we introduced, and psi is given by minus omega alpha star into F alpha theta by 2 omega alpha star into H alpha. So the new Lagrangian is related to the old Lagrangian in a nice way. Now the interesting feature is that if you change psi to some another arbitrary function, still that's a sensible point to start quantizing your theory. So that's an interesting structure which you don't see when you do the Fadio-Popov. When you do the Fadio-Popov, you feel that okay, there is a freedom. There's a freedom in choosing F alpha and B, and that reflects in the BRST formalism in the following way. You can start with the classical Lagrangian and then add any piece which is a total derivative with respect to the fermionic operator psi. So changing psi to psi tilde can be or will again give you a consistent point to start quantizing your theory. So BRST symmetry is not the end of the quantization, it's actually the beginning of the quantization. So let me.
Given any gauge fixing constant, you can share the Taubman with this combination.
Yeah, right.
So that you are following with your gauge fixing conditions.
Yeah, for the psi. Now that's an interesting thing. So we found that once you try to make path integral sensible for a gauge theory, you get into a new Lagrangian, and the new Lagrangian has an I symmetry, which is the BRST symmetry, And then we said that, okay, BRC symmetry is a global symmetry. Now, when you have a global symmetry, we should utilize it properly. So what you can do is the following. So you can try to analyze the implication of BRC symmetry for a generating function. So what is a generating function? So we know that we are going to use path integral for computing time ordered correlation functions. So which can be thought of as computing the expectation value or the correlation function for different fundamental fields in your theory. So you have fields A mu, psi, and ghost fields and the auxiliary field. You want to compute the correlation functions between them. So a generating function is a convenient way to construct all these correlation function in in one step. So it's again a path integral d a mu d psi bar d omega. So all of them are functional integral for each field. D omega star dh, and then you have to look into you have the action piece. Now when you are considering a generating function, you have to modify your action. So you have the new Lagrangian plus chi n into jn. So you have to introduce a source piece. So let me tell you what is chi tilde n. Chi tilde n is a notation which I collectively use for denoting any of the field a mu alpha, psi, l, omega, omega star, and h. Inside chi tilde n can be any of this field. And for each field, we can introduce a source term. And once you are able to compute this object, you can extract all the correlation functions. So that's why it's a generating function. Now we would like to know what is the implication or what is the effect of BRST symmetry on this generating function. I mean, these are global group and they have finite. It's a global symmetry. That's true. Right. Right. So it has an effect on the spectrum. So when you compute the spectrum for the theory, so if you have two states that are related by BRC transformation, you have to, choose one of them. This itself is a consistent, well-defined expression. So this is a finite expression. You don't have anything to, you don't have to worry about any more thing. What this symmetry does is that it introduces some relations among the correlation function that you compute. And that's what I mean by saying that, what is the effect of BRC symmetry for this generating function? So it somehow encodes all the relation that, or it knows about all the relation between different correlation function. So that's a goal. Can we find an identity that's satisfied by the generating function? And that identity is known as Slavnov-Taylor identity. So this is an identity satisfied by the generating function, and the source of this identity is the BRC transformation or the BRC symmetry. and what is their identity. So what you can do is you can start with Cj, which is defined in terms of a path integral over dA mu nu alpha, and then so you have the remaining pieces here, and then what you can do is you can try to do a gauge transformation. A can be transformed to a prime alpha mu, and then the remaining piece. And we know that due to the, it has the symmetry. So these two things should be equal. When choosing a mu or a prime or a prime won't change your generating function. So that's a simple statement. So how these a mu and a alpha mu and a prime mu alpha are related? So we already gauge fixed it. So these two are related through a BRST transformation. So you have a relation between a prime alpha mu and a alpha mu. So if I take these two things and look into the difference, that's a BRST exact piece. So it's clear that the generating function has a BRST symmetry. So these two objects should be equal, and that itself will. This is the statement, and this will give you an identity, because you know that a prime alpha mu is equal to a mu alpha plus some piece, and this can be utilized to figure out the Slavnov identity. In general, Slavnov identities are for full gauge symmetry. And anyway, BRC symmetry can be thought of as the global part of the gauge symmetry. So the usual Slavnov identity is valid even for the BRC transformation. The only thing what you have to do is you have to really, you are not supposed to consider the general gauge transformation. Instead of, you have to consider a gauge transformation that is constructed using ghost field and this theta parameter that I was mentioning. So the final identity can be easily derived, and the identity is the following. So to state the identity, we have to introduce another object. So Cj, I denote it by e raised to I omega j. So this is the definition for Wj. And I can take this Wj and then do a Legendre transformation. So that gives you the effective action, or the 1PA effective action. So gamma chi, so we know that J are sources for fundamental fields in theory, and I denoted the sources, or denoted the fundamental fields by the notation chi. So what you have to do is you have to somehow get rid of the source term. So you do a Legendre transformation and then obtain the effective action gamma chi, and the precise relation between W and gamma is as follows. So you have Wj chi, where j chi is the source corresponding to the field chi, minus d4x chi and jn chi. So this is a simple Legendre transformation, and Legendre transformation of W gives you the effective action. And I'm going to state the Slavnov identity in terms of effective action. So we are considering all possible fields in chi n. So it could be fermionic field or it could be bosonic field. So when I define a derivative for chi n, I should be very careful. I should explicitly state whether I am going to use this derivative for acting from the left side or acting from the right side. So you have two derivatives. One derivative is a derivative that you act from the left side on some function gamma, and then there can be another derivative that acts from the right side of the gamma. So these two are related in a simple way. So so this is the relation between left derivative and right derivative if chi n is a fermionic object. For bosonic object, it doesn't matter. So you can go ahead and then try to and write down the Slavnov identity. So before writing down the Slavnov identity, let me introduce another notation. So I said that we are going to do a BRC transformation using theta parameter, and the action of delta theta chi n can be written as theta s chi n, and I'm going to just denote s chi n by some operator delta n. I mean, these are just introducing more and more notations. And there's no physics in it, but it will take you to a convenient form. And you can derive the Slavnov identity from this observation that when you use, I mean, it doesn't matter which representation of field that you use. I mean, you could use a field representation A alpha mu, or another field representation that is related to A alpha mu by a BRC transformation. And this is a trivial statement, and from this statement you can get the following identity. So you have to compute an expectation value for this piece without turning off the source. With the source, you compute the expectation value, and then multiply with the left derivative of gamma with chi n x. This is equal to 0. So you take the effective action and then consider left derivative with respect to the field chi n, and then multiply with the expectation value of delta n, which is just BRST variation of chi n, and then integrate it over the whole space-time. So that should be equal to 0. So this is a consequence of BRST transformation. A consistent effective action must satisfy this equation. This is a trivial statement that the effective action is invariant under BRC transformation. And this is the Slavnov-Taylor identity for BRC transformation. Now this itself is not the thing that we want. We want to go ahead and then introduce a source for the BRST variation itself. So we introduce a source for the field, but didn't introduce a source for the BRST variation, right? But when the relation that BRST symmetry introduced involves inserting BRST variations in correlation function. This is what I mentioned initially. So you did gauge fixing and then did all the exercise and then obtained a new Lagrangian, and the new Lagrangian has a BRC symmetry, and this BRC symmetry, I said that is going to introduce certain relation between correlation functions. See here, I have a derivative acting on the effective action with respect to chi n. So when you do a derivative on effective action with a field, that's going to introduce a correlation function, right? And then take those correlation function, multiply with the BRST variation, and then integrate over whole space-time. So this is actually a relation between correlation function, which involves BRST variations. So whenever you have a correlation function involving BRST variation, it's useful to introduce source for that composite operator, right? So you let's say you want to compute correlation function for some composite operator On. So the easiest thing to do is, or the convenient thing to do is, you introduce a generating function which can generate that correlation function, right? For that you have to introduce a source for that particular composite operator. So here the composite operator is a BRST variation itself. So it's sensible to introduce a source for the BRST variation. So we denoted the source for the field chi n as J. Now we can introduce a source for the BRST variation delta n, and then I denote it by K. So this is a source for BRST variation. That means we are going to introduce a more general generating function. So initially we had a generating function Cj. Now I am going to make it into a generating function that has two sources in it, or two class of source in it, J and K. Then here I have to add the additional source term. Now we can go ahead and ask what is the implication of PRSC symmetry for this generalized generating function. And again, this satisfies the Slavnov identity. But the only difference is that instead of having a source J, you also have a source K. So you have to generalize it with Jk, and then everything else is same. So remember, I'm trying to figure out a relation satisfied by the generating function. So when I introduce more sources, then I have another set of relation. So this is not just a correlation function. This is a function or correlation function that you compute with the source in it. So it's more than just a correlation function without a source.
One side of the would be independent of the one side you already had because S of chi n would be some of the old fields, I mean, that we already had.
Yeah, it's the same field. S of chi n is again the same field.
S of chi is going to be, yeah, it's going to be
the same BRST variation.
Sum of some chi's.
Yeah, yeah, that's true. Even product of some chi's.
Sure, but so you get something more by introducing the.
No, the S chi n is same, but the expectation value you are supposed to compute with a action having extra source term, not just with J, right? So this extra piece is there. So initially you computed the expectation value only with this much of Lagrangian, right? So you have Lagrangian, new Lagrangian plus the source term. Now I'm saying that I'm going to turn on another source, which is just delta nkn. Yeah. So that's why it's more general. It has more information. So when I switch on one more source, it starts having more and more information about correlation functions, right?
I don't see how it would give more information as opposed to what we already had.
So see, if I compute Cjk, then I don't have to really go and again compute delta nk, right? I know the expectation value of a correlation function involving only the only the external, only the fundamental fields, right? So when you have Jk, I also know that what is the expectation value of a correlation function that involves fundamental fields plus the BRST variation. So that's more information. You can actually compute. That's true. So you don't have to again. I mean, once you know it, you don't have to do one more calculation. You already know this answer. If you only know Cj, you have to redo the calculation and then compute what is delta nk. Right? So that's why I'm saying it has more information. I mean, it's true. Like, I mean, once you introduce more and more sources, it's equivalent to saying that you know about more and more number of correlation functions. So anyway, so you can find the identity satisfied by the generating function with sources j and k. And the interesting thing is that again you can define a wj. But with the source k, so you have wjk, and then do the Legendre transformation for k, and then get an effective action with sources j and k. And one can show that this piece delta n chi is an expectation value for BRC transformation with sources j and k is equal to right derivative of effective action with kn. This is a thing which you can compute without much. Without doing a lot of things. It's a simple statement. It's a statement of related to the Legendre transformation. And once you have this observation, what you get is the Slavnov-Taylor identity takes a nice form. So you get something called Sin-Justin equation or Justin identity. So the identity is that you can start with left derivative of effective action with respect to the fundamental field chi n, and then multiply it with the right derivative of chi with respect to the source for the BRST variation kn, and then integrate it over whole space time. This should be equal to 0. So here what you gained is that you found that there's a symmetry between the fundamental fields and the source for the BRST variation. That's an interesting observation. So that's equivalent to saying that the role of source for the BRST variation is more than what you really expect. So it's almost, it has a role similar to that of fundamental field. So that's a nice observation. Here, yeah. So gamma is a function of j and k.
So you have to also subtract for x k times something.
Yeah, that's true. So you have to do a Legendre transformation for each source, right?
So here fundamental fields are BRST closed, right? Then delta n.
Yeah.
S times chi n. S chi n.
Yeah, S chi n, right? Delta n, right?
So if you calculate C j and you calculate C k.
Yeah, C j k. Yeah.
Suppose you calculate C k.
Yeah, yeah.
Are they related by some BRST operator? Because their fields are BRST closed.
Right. I mean, it's not just BRST related. So one side you have a field itself, and the other side you have the BRST variation itself, right? It's not chi n plus S chi n. So these two are two things. I mean, it's something which is unexpected. You never thought that a source is going to play the similar role of the. I mean, a source will have a role that's similar to that of fundamental field, right? It's a nice symmetry, which is not expected, and that's what you see in Sinn-Justin equation. So you can go ahead and then make the symmetry manifest by introducing something called anti-bracket. So today I won't define that, but so you can define something called an anti-bracket, which with for function f and g. So assume that f and g are same, say gamma gamma. So the anti-bracket gamma gamma is exactly equal to this expression. So I mean, this is something which I haven't explained properly, but I'm just mentioning that you can introduce another definition, the so-called anti-bracket. And in terms of anti-bracket, this equation is equivalent to saying that anti-bracket of gamma with gamma is equal to 0. So BRST transformation or the BRST's invariance start giving you nice relation between infinite number of correlation functions. That's what you mean by an identity satisfied by the generating function or the effective action itself. So that means the BRST symmetry has a big role to play, and the source of BRST transformation also have some more thing to do than you expect, and that's the starting point of BV formalism. So what BV formalism do is it start from Sinn-Justin equation and then utilize or think of BRST symmetry as a fundamental principle. So you, instead of starting from unfixed gauge, unfixed action or classical action and then do the gauge fixing, what BV formalism try to do is start from an action that has BRST symmetry in it, and then just go ahead and quantize it. And this has additional or the BV formalism has additional advantages. So here I started with a gauge theory having gauge group G, which is closed, which has closed algebra. That means if I consider consecutive gauge transformation, that's again another gauge transformation. Now you can consider gauge transformations such that, or the gauge group such that, if you take the commutator of two gauge transformation, it could produce a gauge transformation plus a piece that vanishes only on classical on shell, or only on shell, or a piece that's proportional to the equation of motion. So these kind of algebras or Lie groups are known as open algebras. So closed algebra is a special case of gauged algebra. You can have a more complicated situation where your algebra won't close, and Faddeev-Popov method is not efficient or is not useful for condensing such theories. And even you can go ahead and then you can consider gauge theories that are so-called reducible gauge theories. That means you can have gauge invariance, which itself has another gauge invariant. So you can go. I mean, you can consider more and more complicated gauge theories, and you can't use Faddeev-Popov method for doing the condensation. But if you start from the BRC symmetry and then quantize it, you can do almost. I mean, you can quantize almost all theories that have a Lagrangian description. So BV formalism is an extremely powerful method for doing the quantization, and string field theory really require that. And string field theory has a gauge structure which is very complicated. I mean, the gauge group of string field theory, say for closed string field theory, it is so complicated that it has a open algebra. The structure constants itself will depend on the fields in the theory, and it won't close. It's actually the most complicated gauge theory that you can have. So such a complicated gauge theory you can't quantize using the usual Faddeev-Popov method. So you require BV formalism, and that's the reason why I was trying to motivate BV formalism. So the main point is that for BV formalism, BRC symmetry is the fundamental principle, and you have to really take the sources for the BRST variation more seriously. So that's the end of today's talk.